Dante Certification Program Level 3. This module takes a deeper dive into IP subnetting and IP addressing. The worst part of IPv4 addressing is the confusing mixture of binary and decimal. This makes it more difficult to learn IPv4 subnetting than it really should be. An IPv4 address is 32 bits long. This means there are more than 4.3 billion possible unique addresses. It is written using a dotted decimal notation, which in and of itself is actually quite confusing. We write decimal numbers AA, BB, CC, DD, giving decimal values for 4 octets. We know an octet is a number consisting of 8 bits, and that gives us a potential range of values from 0 to 255. If I really want to convert binary to decimal, there's plenty of good tools out there for that. Windows Calculator is really good. Mac OS has one as well. In fact, any scientific calculator would do this conversion for you, so you don't need to do it all in your head. Using decimal notation in this manner is actually counterintuitive. So, for example, the device number after 255 should be 256, not 1.0. In a decimal world, we'll count 253, 254, 255, 256, 257, 258, and so on, not 254, 255, 1.0, 1.1. That would be kind of strange. So in binary, the address after 111.111.11 is 000.000.000.000. Now, instead of reading this out as a whole bunch of zeros and ones, we could actually change this in hexadecimal to 0100 to make this slightly more understandable and easier to write out and read. Computers, and therefore networks, use binary fundamentally. IPv4 subnetting makes a lot more sense in binary than in decimal. IPv6, for the same reason, is notated in hexadecimal. So here's a quick refresher on binary. Now, with 1 bit, I can have 2 potential values, a high and a low value. Conventionally, we represent these as ones and zeros. With 2 bits, I have 4 potential values. They are 00, 01, 10, and 11. Likewise, with 3 bits, I can have 8 potential values. This pattern follows a simple mathematical pattern. That is, powers of 2, where 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8, and so on. But in the case of binary, these place values are a little different to decimal. If you go back and remember how you learned to count, you might recall counting by row from, say, 1 to 20 over and over again, and then you get this idea of a pattern in increasing numbers. Then from there, you were given hundreds and tens in units as counters, and we came into the concept of a place value. This is true in a binary system as well. In decimal, we have 10 different symbols to represent the value of each place. So I could have the value 0 through to 9 in my ones column, and then repeat that in my tens column, and so on. In binary, because binary only has 2 states, a high and a low state, I can only represent one of 2 values in each place column. So I get different place values in a binary system. We take it for granted in a decimal system that 123 is arrived at by 1 multiplied by 100 plus 2 times 10 plus 3 times 1, which simplifies to 100 plus 20 plus 3, which gives us 123. Similarly, in binary, in order to convert this to a decimal system, we would do this, which will then simplify to 64 plus 32 plus 16 plus 8 plus 2 plus 1. An essential element of using IP is subnetting. Now, using IP, we can describe a single node as using an IP address. We can also describe a group of nodes using an IP address as being a member of an IP address, in this case, a network IP address. To understand whether an IP address refers to a group, a network, or a single device, we use an IP subnet mask. The IP subnet mask is crucial for a device to understand whether it's connecting to a device in its own IP subnet, which would be a local transaction, or whether it's connecting to a remote IP address on a remote network. On a local network, the device can communicate directly. This means the sender can construct an Ethernet frame and will communicate with the receiver directly. This means the sender will ARP the receiver directly. For more information on how ARP works, please refer to the ARP module in this course. In order to connect to a remote network, the device knows it can't ARP the receiver directly, so it will ARP the gateway so that it can pass that message via the IP layer, that is layer 3 of the OSI model. The IP subnet mask is held in all devices in a network. It's used to define the size of the local area network. A device applies a logical truth table to determine if a local or a remote destination is the one that's being requested. In this case, it will be 1 equals true and 0 equals false. Now, this is based upon the masks, so I will compare my sending IP address with my destination IP address, and I will compare them with the mask and use the zeros and ones from my truth table to work out whether the address is local or not. In IPv4, our IP subnet mask is the same length as our address. Now let's talk about classful IP addresses. Once upon a time, there were no IP subnet masks. IP subnet masks were implied by the class of IP addresses. The classful IP subnet extinction event was IETF RFC 1519 in 1993. Now, how many of us were using public internet in 1993? Not many. So why are we interested in classful IP addresses? This was somewhat of a hangover from the way backwards compatibility was worked out. We were dealing with number pattern in old days. It's true, since 1993, modern IP has no class. But to continue with the theme of patterns, we look at modern IPs this way. A Class A IP address always starts with a 0. A Class B IP address always starts with a 10. A Class C IP address starts with a 110, and a Class D IP address, which is multicast, always starts with 1110. This means, by extrapolation, Class A addresses start at 0.0.0.0 and would go all the way to one address before Class B starts, which would be 127.255.255.255. Class A networks have a default subnet mask of /8. That means they are 8-bit subnet masks. Class B addresses start at 128.0.0.0 and go up to 191.255.255.255. Class B networks have a default subnet mask of /16. Class C addresses start at 192.0.0.0 and go up to 223.255.255.255. So an IP subnet has its own address. This always ends at binary 0. An IP subnet has a broadcast address. By convention, this always ends at binary 1 for all host bits. So if classful IP addresses are extinct, why do we talk about them? Is it because dinosaurs are cool? No, there's an indirect legacy to clean up here. RFC 1918 defines private IP addresses. These are essential to make the IPv4 internet work. They are defined in the standard as /n modern CIDR notations, so that would be the number of bits in the IP subnet mask. RFC 1918 private IP addresses have an IP subnet. They are not classful IP addresses. However, they are also called out in backwards compatible classful terminology. This is where the legacy confusion stems from. Now let's look at an IP address we're all familiar with. Take 192.168.1.1. Let's translate this to binary. we get this string of binary digits. Now let's apply a familiar subnet mask. This gives us this string of digits. We can see here that this is a sequence of 24 ones followed by 8 zeros. In the subnet mask, 1 means must match and 0 means may match. Let's send this to a destination now, 192.168.1.2. If we compare the binary of the source and the destination and apply the subnet mask, we can see the binary parts match all the way down to the last 2 digits. This means we are in the same local network. Through this, we know that our transmitting devices can ARP for that destination and can acquire the MAC address for the device because we are in the same broadcast domain or IP subnet. I can extend the subnet mask, which means I can make more but smaller subnets. I can take 192.168.1.1, then translate that to binary, which would give me this. Then apply a VLSM, that's variable length subnet mask. This time I'm going to apply a 25-bit subnet mask. Now you can see instead of 255.255.255.0, we have 255.255.255.128. As we know already, in the subnet mask, 1 means must match and 0 means may match for the destination to be local. This means we have actually shortened the IP subnet by 1 bit. Now instead of having 256 potential values in the last octet, we have only 128 values. Now we compare this as we did before, and we can see that this too is local. I can also shrink the subnet mask. That means we have fewer but larger subnets. Let's take 192.168.1.1. Translated to binary, it gives us this. Now we apply VLSM. Here we are using a 23-bit subnet mask. This would give us this. This means each of our subnets can now be 512 devices. Once again, we know 1 means must match and 0 means may match. So if we send it to 192.168.1.2 and we compare it as we did before, we can see that this too is local. We can see these magic numbers in an IP subnet mask in the far left-hand column in this chart. We can see the bit structure that makes them up. So for 0 to be in an octet, we have all the bits turned off. As you can see, for 255, we have all the bits turned on. We look at 1 octet at a time to create decimal notations. Here we can look at the CIDR number of whichever we call the significant octet. For example, if we're looking at a 8-bit 255.0.0.0, we can trace down 255, go across, and we can see CIDR first octet is 8. If we want a 16-bit subnet mask, we do 16. So why are number patterns interesting? When network equipment was slower, these patterns helped with processing reduction. By doing so, they helped increase speed. Let's compare some examples. If we have a subnet mask of 255.255.255.0 and a network address of 192.168.1.0, we can actually see that all of our host bits are set to 0. This means that's our IP subnet address. Our first host will be 1 more than the network address. Our broadcast address will be all the host bits turned on. Our last host is 1 less than the broadcast address. Here's a much smaller subnet mask, 255.192.0.0. Here we see our network address. Our first host, which is 1 more than that, and our broadcast address. Now our last host, which is 1 less than our broadcast address. So IP subnet masks in binary are much easier to look at than doing them in decimals.